Okay, so with our next topic, we're actually getting into putting together some of the topic concepts from the previous chapter about sort of what are the behaviors of atoms. And now we're getting to the point where atoms are going to come together and make compounds. So that's kind of like we're starting to get into the traditional sort of stereotypical chemistry fantasy where you see beakers, you see mixing things, and we're making new materials. So that's kind of starting today now that we have sort of the foundation set. That required that we understand the behavior of atoms from last time. So in this case, we're going to be putting them together to form ionic compounds, and the term itself might give a hint at what we're going to be discussing. Compound means made of more than two types of elements, and ionic sounds like ion. So it might be two types of elements making ions into a substance called a compound. Whoops, there we go. So it all goes back to the ideas that we started early on in the class about positive and negative charges. The idea is that there are two things happening when atoms come together to make compounds. The first is that we saw as the very tail end of the last lecture, the very end, we talked about predictable ions, and they are based off of their electron configuration. So we have, and sort of symbolically, we say that unless the number of electrons matches a noble gas, we think of atoms as incomplete. If they have room in their orbitals, or if they have room to create orbitals, they would like to do so that they finish a shell of electrons. And so the noble gases are the ones that have those shells that are completed. And so all atoms are trying to adjust their electron count until it matches the closest noble gas that they're related to. And so this is how ionic compounds, our first kind of compound, is formed, because there are some elements that would like to lose their electrons to become like a noble gas. And there are some elements that would like to gain electrons to become like a noble gas. And so what we see is that if we partner up an element that would like to give away its electrons with an element that likes to gain those electrons, then they'll naturally do that. And that's what results in making ions that will form ionic compounds. So it all has to do with we're matching one element that likes to give with one element that likes to take. And from that, we make a new substance. And so we have to utilize our periodic table one more time to figure out which elements like to make positive ions or cations, which elements like to make anions, so that we know which ones to pair up. So just using those labels that we had for the periodic table, main group, transition element, metal, non-metal, which elements, just generally speaking, not very specific, which elements like to make those cations, those positive ions? Or which side maybe of the periodic table? Let's start with which side, left or right? So cations are those positive ions. So I think, oh, we're kind of split even right now, left and right, left and right, left and right. So it's going to be the side that likes to give away those electrons and make the positive ions. So those are the ones that are on the left-hand side. And so if we're giving the label metal or non-metal, it's going to be metal, which is on the left side. And if we're pairing that with elements that like to make anions, we're going to pair it with non-metals on the right-hand side. Remember those terms? So remember, for example, the first group, the first column of the periodic table, the alkali metals like to make the +1 ions. So they're an example of the left-hand side wanting to make those positive ions, whereas the second to last group on the periodic table are the halogens. They like to make the -1 ions. So what it tells us is that we're going to make compounds out of an element on the left-hand side matching up with an element on the right-hand side, because then we'll have a pair where one element would like to give away its electrons and another element would like to take those electrons. So what actually happens when those elements come together? Well, I mentioned that they form what's called an ionic compound. How does that actually happen? So we can think of it happening in steps. I have two atoms here, and there's going to be an electron transfer between the two. A metal likes to give away its electrons, making positive ions, and a non-metal would like to take those electrons, become negative. So there's going to be a transfer that's occurring here. So in this case, there's going to be a natural, the electron is flying away. So when this happens, the metal becomes happy because with less electrons, it's becoming like the noble gas neighbor it's closest to. Whereas the nonmetal is becoming like its nearest noble gas neighbor because it is gaining those electrons. So we can actually sort of talk about this in terms of, say, an example, and I go through an example in the pre-lecture videos. So something like lithium and fluorine, we can say, well, how do I know that lithium is going to want to give away its electrons and fluorine is going to want to take those electrons? Well, we can start with their electron configuration. So help me out here. What is the electron configuration for lithium? So again, we're going to have to look at our periodic table and do the starting with hydrogen. We're going to count the squares until we get to lithium and then do it again for fluorine. So that's going to be 1s, and we count the squares, 2, 2s, 1, right? For fluorine, we start back at the beginning again and we count. It's 1s2, 2s2, 2p5. So when I make the lithium ion, we know that the predictable ion of lithium is going to be the positive ion because we memorized it. But we see that to do that, it's going to have to take its valence electron, its last electron, and give it away. So what does its electron configuration look like now that it's given away an electron to become an ion? Well, now it's just 1s2. What does 1s2 remind you of? It should remind you of a different element. This is helium. So when I give away an electron from lithium, I become like helium, my nearest noble gas neighbor. So this is why lithium and all the other alkali metals like to make +1 ions. They become like their noble gas neighbor. And then we can do the same analysis with fluorine. Fluorine would like to make the -1 ion. And so its electron configuration will go up by 1 electron. 1s2, 2s2, 2p6. Now, does this electron configuration remind you of a different element? It should. It's neon, its closest neighbor noble gas. So naturally, the metal and the non-metal want to transfer their electrons. When they do that, they become happier, and it's like literally where we can think of it, there's sort of like an opening in their shells, and they're patching it up, they're fixing it, they're completing their shells. And they do that to look like their noble gas neighbor. So that's only half the story. What happens once this transfer occurs? Well, now we have a positive charge and a negative charge. And what's going to happen between those two? They're going to attract each other. So we call that an electrostatic because it's electrical in nature. That's what we call it, electrostatic attraction that pulls them together and makes them stay together. And so when they're stuck together as ions, and in the case we can talk about lithium and fluorine in this case, then they're held together, they're bound to each other by what we call a chemical bond. In this case, because it's two ions attracting each other by positive and negative charges, we call it an ionic bond. So this should sort of break down nicely for us. Bond means a connection, and ionic means having to do with ions. So an ionic bond is the attraction that holds positive and negatives together in an ionic compound. It's that attraction between two complementary charges. And so that's going to be the theme of all of these compounds. We have positive ions and negative ions, and they're going to come together and form ionic bonds that hold them together. So it's not just a passing thing where it's I transfer to you and now I'm going to walk away, but it's actually they transfer, and after that transfer they're like, hey, you're positive, you're negative, we're going to stick together. And so afterwards they end up sticking to each other, and they stick through what we call the ionic bond. Okay, of course, let me know when I need to slow down. One thing to note is that, remember that I mentioned that charged particles have an electric field. What that means is that from the center of one of these ions, there is attraction that potentially could occur in all directions. Since each ion is a circle, basically, because all of the orbitals kind of meld together, they kind of overlap on each other, it basically becomes circular. Because they're symmetrical in all directions, they look the same in all directions, it means that we don't have to stop with one partnership. And in fact, here I have 4 ions. There is no reason why the right-hand side of this ion can't attract another complementary charged particle. So that's exactly what happens. When we combine 2 elements in a beaker, it kind of snowballs, and snowball means it just builds on itself, sort of keeps going and going and going. So we say that ionic bonds are non-directional because my free end right here, this opening, can allow attraction to another set of ions. And so we're going to build over and over and over again until we get complete sort of coverage, if you might say it like that. So it'll end up being minus, and in most cases, it's a very nice sort of pattern here, right? And so plus, so they're going to attach each other and sort of stack over and over and over again. So there might be more over here as well. So that's what I mean by snowball. Like it just keeps building and building. Like if you were making a snowball from snow, you sort of pat it and you keep building until it becomes a huge, snowman kind of a thing. So this is what happens when we form ionic compounds. We get this nice pattern. Eventually, we get this repeating structure that keeps going until we run out of ions. So what I'm drawing here should start to look familiar to you when we go back to our ideas of matter. What did we call the phase of matter that kind of looks like this? So this kind of stuff should remind you of, yeah, so we're getting it, yeah. So it's crystalline solid. So this should remind us of a crystalline solid. And so in fact, that's something that we can predict based off of what we understand about atoms that become ions and how ions can attract from all sides of their sphere. So again, so this is the beauty of chemistry. By understanding the tiniest specks of matter, we start to make predictions about everyday materials. And our first prediction that we're really getting out of chemistry is the fact, well, metals like to become ions, positive ions. Nonmetals like to become negative ions. When they get together, they'll start packing into little crystalline structures. So we might predict that ionic compounds are predominantly crystalline solid compounds. And so can we verify that with a set of data is one idea. Well, let's take a look at some examples of ionic compounds versus everyday compounds. So what I have here are some examples of ionic compounds, and it's important to be able to be flexible with terminology. Ionic compounds are often called salts, and maybe that should start to make a little more sense with our discussion, because salts are crystals, like table salt. What we see here are the melting points of several different kinds of ionic compounds. And this is in degrees Celsius. And just, it could be hard to sort of see what the meaning of these numbers are. So to contrast that, I put some common substances, like the melting point of water is 0, butter, 35, candle wax, sugar. And to compare to ionic compounds, what do we see about their major difference? It should possibly be an obvious difference to us, hopefully, between ionic compounds and common other substances. Yeah, it's as simple as ionic compounds have incredibly high melting points. So again, this is something that's going to recur from this point of the class onward. It's the idea that by knowing about how atoms fit together, we get insight, we can make predictions about everyday matter. And so our first prediction is that ionic compounds are kind of these like magnets in a way. I don't know if you've seen those magnets that are like little beads, and so you can make those really cool shapes out of them, but it's literally, does anybody know what I'm talking about? It's like, they're like these little spherical magnets, and they kind of like stack, right? And I don't know if you've seen, but like some people make incredible art with them. Like they make these like the Eiffel Tower and all that stuff, and it's all out of magnets. But that's literally what's happening when we make ionic compounds. We have a metal and a non-metal transferring their electrons, and the resulting ions start to stick to each other by what we call the ionic bond. And because ionic bonds are non-directional, meaning I can attract from every direction, it means they'll all start sticking in 3 dimensions. So from the left, from the right, the up and the down. And so eventually we get crystalline solids, and we see that because they have such high melting points, they're really stuck together. So that's going to be our first kind of aha moment. It's that because ionic compounds are really stuck together by these strong plus minus attractions on all sides, we are going to have very high melting point crystalline solids. So that's the first kind of wow. When we call them salts, it can sometimes be a little bit, it can sometimes be like, what do we mean by that? So just to sort of demonstrate that ionic compounds should have the name salt is because much like table salt, if you look at it under a microscope, you see that these sort of connections via these atoms and their charged, their non-directional ionic bonds, we start to get incredibly interesting geometries. And so what we see is that over the course of different kinds of ionic compounds, because it all stems from one positive to another negative, to another positive, to another negative, because it's such a sort of predictable kind of geometric idea of just, if you have room on your sides, you can still stick more. We get these incredible sort of beautiful crystal structures, which can vary based off of how big or how small each ion is. So we have some very sort of sharp angles, because it all stems from the original geometry of how does a positive ion attract a negative ion, and is that going to attract from an angle, or is it going to attract sort of in a different, at a different angle? And so among all of the ionic compounds, we see very interesting crystal structures, which we call a crystal lattice. So a lattice is kind of like another word for like a scaffold, like a sort of skeleton to build on. So the skeleton can range from being cubic. So maybe I should say kinds. We can have cubic, and it can vary, depending on the compound. We have what's called rhombic, which looks like a rhombus. Let's see, bic. We have hexagonal. That all depends, but the point is that because of these ionic bonds that are sort of like like those small little magnets, we can get very interesting geometries that result from the little geometries of the original ions. So if the original ions start forming a cube shape, then as it snowballs, it's always going to keep that cube shape. And so, for example, cesium ferrioxalate is sort of cubic looking, and so is potassium periiodate. So we have those little interesting sort of results that come from it. Now, one thing to note, and this is something that gets confusing among students a lot, is the idea that ionic compounds actually don't have molecules in them. Remember, the idea is that each ion attracts neighbors from all directions. So if I were to say, ask what is the sort of molecule that you see here, and maybe it's a little bit easier to sort of, or maybe it's easier to see that it's hard, if that's a way to say it. If I were to ask you, pick out a single molecule, a single particle that represents all of the atoms stuck together, it's actually incredibly difficult, to the point where it's impossible to say which ion is partnered with which. Because if you imagine that a positive ion is trapped between all of these negative ions, well, I know that one positive might want to attract one negative, but which one of these would I call the partner of this positive ion? Because they all look the same, it's impossible to say that there's a molecule of this one plus with one minus. And even if you wanted to argue that it is possible to say that there's a one plus with one minus, what I like to do is I like to spin the page and say, now, do you remember which one was the partner? And so the answer is it becomes impossible to figure out which one is the actual partner. So we say, because everything looks identical from all angles and all sides, there really are no individual molecules in an ionic compound. And that's going to contrast to the other type of compounds we're going to talk about, which are going to be molecular compounds and acids. Those will have molecules. And the difference is that in our particle picture, I can pick out a single water molecule from a lineup from all of the particles. But with an ionic compound, I can't do that. because from all directions, they look the same. So there are no distinct particles in a salt crystal. It only has what we call an empirical formula, or what we call a formula unit. So formula unit is just a synonym, means the same as empirical formula. It's just used for ionic compounds. They mean the same thing. So we can't say that, for example, NaCl has individual NaCl molecules because they all kind of look the same. Plus, minus, plus, minus, plus, minus. There is no single particle of Na with a Cl that I can identify. So for this reason, and that's why I emphasized this in our previous lecture, for this reason, ionic compounds are only described by empirical formulas. And that's going to be different when in the next lecture, or next two lecture, that we talk about when we talk about molecular compounds, which can be identified with a molecular formula, because we can identify those. So for ionic compounds, the chemical formula is their empirical formula. That's the only thing we use to describe them. And remember, it's the lowest ratio of the elements. So if it's 2 to 4, we just reduce that, pull out the 2s. And then it becomes a 1 to 2. So because we're talking about ions here, positive and negative ions, for ionic compounds, it's the lowest ratio of their ions that creates an electrically neutral combination. So it's basically how many positives do I need to match with how many negatives so that I can get a neutral overall particle. Because as we know, salt doesn't zap us with electricity if we touch it. It's electrically neutral. And if I need to explain a part again, please let me know which part specifically, and I will do that. So what this means is that when we have NaCl for table salt, we need 1 sodium per 1 Cl. And in terms of the other aspect, it's because each sodium atom carries a 1 plus charge, and each chloride carries a 1 minus charge. Then the lowest neutral ratio, oops, not ration, there we go, is also 1 Na to 1 Cl. And that's because sodium carries a +1 charge when it becomes an ion. Cl makes a -1 charge. So the lowest empirical formula we can have, well, if this is a +1 and this is a -1, then a 1-to-1 ratio will make them neutral. So that's kind of the key here. For ionic compounds, sum of positive plus sum of negative have to equal 0. And that's going to be a key kind of trick that we use to solve problems involving ionic compounds. Well, the formula needs to be such that all of the positives in the formula and all of the negatives in the formula have to be neutral overall. And so that is sort of the key way that we do this. Okay. And this is also why, we have these, we say that this crystal lattice doesn't have molecules because there are a lot of positives and negatives. We just look for, well, what's the lowest ratio of positive to negative to make an overall neutral substance, because they all kind of just stack all over each other. Plus, minus, plus, minus, plus, minus. There is no molecule because there is no partnership that we have with one specific in this case, negative. This positive is kind of partnered on all sides with all of these negatives. So it kind of becomes confusing to think of a sodium chloride particle. Instead, we think of, well, the lowest ratio that I have among all of this crystal is a 1-to-1. And so that is a true statement that all ionic compounds will have zero charge. If they didn't have zero charge, then they're not an ionic compound, they're just an ion. Right? Because ion is something with a charge, a combination that has zero charge. Well, it's either an atom, a molecule, or a compound. So this will always be true for an ionic compound. All of the positives and all of the negatives will have to match to be zero. And we're going to use that to our advantage when we try to predict the combinations to make chemical formulas for ionic compounds. Okay. How exactly do we do this? Well, we can do this sort of visually and conceptually first. So that's what we're going to do first. But then we're going to go into how to predict ionic compounds in a faster way. So the way that I like to show it first is through Lewis symbol. So remember that a Lewis symbol represents the valence electrons surrounding the outermost shell of the atom. So in case of calcium, the outermost electrons, so the last orbital has 2 electrons. So go ahead and look at calcium one more time on the periodic table. It's in the S block. So its last orbital is an S, and it's the second one in the S block. So it's an S with 2 electrons. So we put 2 dots for calcium. What this means is that as a metal, calcium would like to lose those 2 electrons, because losing all of your dots represents being complete, like the previous noble gas, the one to the left and up. Or well, if you're reading backwards, if you go left and you go back up. So if I pair it with chlorine, I have to ask, so what combination do I need in order to have both atoms be completely happy? Well, we know that calcium wants to give away its electrons because it would like to be like its nearest noble gas neighbor. However, chlorine would like to take those electrons. So we can say 1 dot will be transferred over to chlorine to make the chlorine completely happy. But the problem is that if I only transfer 1 dot, I'm going to be off because calcium has an extra dot. So it's going to need a second partner. So the result is that when calcium atoms combine with chlorine atoms, they're going to form a 1-to-2 ratio because calcium needs to give away both electrons to be happy, but chlorine only needs 1 electron. So we need to have an extra chlorine be a partner. So this is why ionic compounds aren't always 1-to-1 ratios. In this scenario, it's a 1-to-2 ratio. And so we would say calcium and chlorine atoms will form calcium chloride, CaCl2, as the predicted compound. And in fact, if we do the elemental analysis, meaning we take this ionic compound and we return it back to its elements, we would have twice as many moles of chlorine than chlorine atoms than calcium atoms. And so this is how we would predict the exact ratio of the elements that are needed to create these ionic compounds. However, this method, while it does sort of have a sort of nice visual beauty to it, it can take a very long time to actually predict and draw this way. And we want to be able to do this faster. And so we would argue, is there a faster way to do this? Oh, by the way, a question is, does electron configuration have to play a role in this? And the answer is yes, because the electron configuration of calcium tells us it has 2 extra electrons that it doesn't need. Take a look at calcium one more time. Oh, oops, sorry, I'm trying to get the pen to work. There we go. Take a look at calcium one more time. Calcium is, to do the noble gas, save us the time writing. So which noble gas is calcium closest to? So we're looking at our periodic table. It's argon. And we're in the 4th row. So that's 4s2. And chlorine, if we're doing noble gas simplification, we look for, well, which is chlorine's nearest neighbor? That's beneath it. That's neon. And then we say, well, what's left? 3s2, 3p5. So this also explains why calcium wants to give away 2 electrons, because if I give away 2 electrons, electron and electron, then what's left over? Well, it tells me that calcium is going to be just like argon. We've reached a noble gas. Happy face, maybe. Happy face. What about chlorine? Well, it tells us that if chlorine just gains 1 more electron, then it becomes Cl minus neon 3s2, 3p6. And if we take a look at which element matches this electron configuration, this is just like argon as well. So to answer that question, yes, the electron configurations are what's driving this, this strategy of how to do this. Because calcium has an electron configuration where it has 2 extra electrons beyond a noble gas, the easiest way to become a noble gas is to get rid of those 2 electrons and become the +2. Alternatively, chlorine just needs 1 more electron to look like its closest neighbor, argon. So that's why 2 electrons need to be given away by calcium, but only 1 needs to be taken by chlorine. So that means I need 2 chlorine partners to make this work. Now, how do we get this answer a little bit faster? So hopefully that makes sense. If that doesn't make sense, let me know. Because now we're going to just sort of move into doing this faster. Okay, I'm not hearing that we don't want to go faster, so I will try to go faster. The general formula, and this should be familiar if you've watched the pre-lecture videos that I posted. I know there were a lot of them, but this kind of thing is probably the easiest to sort of do on your own, since it really is just reading a bunch of rules. So what we're going to do, the general method to figure out what kind of ionic compound we have, predict the formula. We are going to determine the predictable charges of the ions involved. We are going to write the symbols side by side with their charges. And someone asked a while back about, with formulas, does it matter the order? This is the part where we say, yes, it does. The metal comes first, or whichever ion is the positive ion comes first. Or whichever is the positive ion. And the reason I say that is because there is an example of a positive ion that we learn that actually isn't a metal. So that there's only one, but you know that can be a little tricky. It's a very important one, ammonium. Then what I like to call crisscross method. We crisscross the charges, meaning the charge of the metal becomes the subscript of the non-metal, and we take away the positive or negative sign, and then vice versa. So it's whatever number you have there moves down to the diagonal. whatever number you have on the right-hand side moves down and left and becomes the number on the diagonal. If the subscripts have a common factor, we reduce them. And this is because ionic compounds are always described as empirical formulas, or in other words, a formula unit. But that's the basic method. We write the partners with their charges, we crisscross their charges, and we reduce if necessary. So we can practice. What is the formula of the ionic compound made of sodium and oxygen? So step 1 is to write both of their symbols with their charge of the ion that they make. Sodium is the predictable 1, oxygen is the predictable 2-. We're going to take those charges and we're going to crisscross them. Top goes to bottom here, top goes to bottom here. Those become the subscripts telling us how many of each element we have. There are 2 sodiums for every 1 oxygen. So notice that I did move the 1 down, but for formula purposes, we don't usually write the 1, okay? As I was saying previously, the way that we can check our work is that the positives and the negatives should match, total charge of each should match. So this is kind of a formula, but it's probably easier to just sort of conceptually sort of try it out. It's going to be the charge of the cation times the number of cations plus the charge of the anion times the number of anions is equal to 0. So in this case, 2 sodiums with a +1 charge, 1 oxygen with a -2 charge equals 0. The answer is neutral, as it should be. I have several questions. Oh, some of them are the same. I love it when we kind of converge on the same line of thinking. So the first question, how did I get the formula? So we're doing what's called the crisscross method. We write, so my intention is to write the formula of the ionic compound made of sodium and oxygen. So what I'm going to do is, remember, when they come together, they form an ionic compound, a metal and a non-metal. The sodium and the oxygen will trade electrons until sodium becomes the +1 ion. We know that because we memorized the predictable charges on the periodic table. Sodium is in the first column. Oxygen is a chalcogen, so it's a -2. So the easiest way to figure out the lowest ratio is what I call the crisscross method. We take the numbers at the top and we cross them. The 2 comes down here, the 1 comes down here. If those numbers that we moved have a common factor, empirical formula, we should reduce them. 2 and 1 are fine as is. So we need, according to the crisscross method, we need 2 sodiums and 1 oxygen to make a compound between them. So that means when sodium is mixed with oxygen, the formula of the compound it makes is Na2O. So this compound, sodium oxide, is like a dusty white powder. So that means if I scoop a bit of sodium metal, I say scoop because sodium is actually so soft. Even though it's a metal, it's actually soft enough to cut with a butter knife. So I scoop a little sodium out and I leave it out in the air. I will have the chemical reaction occur between sodium and oxygen so that I get this dusty white powder where there are always 2 sodium atoms per 1 oxygen atom. Or another way to think of it is this powder has twice as many moles of sodium as it does oxygen. And so this would be the formula for sodium oxide, Na2O. Now I got another question, which is, how do we do this if there are more than 2 elements? So when we're predicting when we are predicting the formula of ionic compounds, we're always going to have 2 ions present. It is possible to have 3 ions present, but as far as being able to come up with it out of thin air, sort of, we're not going to do that. So it is technically possible to say you have a compound made out of sodium, magnesium, and sulfate. And so what is the formula? That is something that happens in nature, but we're not going to, with 3 things, there are too many variables at play. So we're not going to, get into that, though it is technically possible to figure it out. It's a more complicated situation. But one thing that you could do is, if I gave you the unfinished formula, NaX Mg SO4 2, you could figure this out because now there's only one variable that we don't know. Solve for how many Na are in the formula. And so if you watch the pre-lecture, you should know what sulfate is, or at least you know of it. Maybe you don't have it memorized yet. That's okay, because we just started. But if you watch the pre-lecture, you know what this means. It's sulfate. And we'll talk about it a little bit later on. It should be possible to figure out this. So predicting the formula of 3 elements, or more than 3 in this case, is challenging. But if I gave you all of them except for how many sodiums are there, that actually could be possible to figure out. And actually, the answer is on this, of how to do it, is on this slide. And so this is actually perfect timing because it's now 11 o'clock. Let's take our break and sort of absorb what we just talked about. So I'm going to leave you with that. Can you figure out how many sodium ions have to be in the formula to make this a complete ionic compound? And so it's 11:03 right now. Let's reconvene at about 11:08, 11:09 to discuss. So I'm going to pause the recording while we do that. Okay, we're back and we have some responses. What is the answer to this question? I'm seeing some good progress. So again, I mentioned that how to solve this problem is on this slide. And the answer is that all of the positive charges must match all of the negative charges. So we look at what are the positive charges and negative charges in here and how many total are there. So in this case, we have sodium, which is +1, but we don't know how many there are. So that's going to be that's going to be our, I hate when that happens. Our 1 times X for sodium has a +1 charge, but there are X of them. I don't know how many there are. There is 1 magnesium, so there's 1 magnesium and it has a +2 charge. I'm not going to write the plus sign. And that has to be balanced with the total negative charges. So we remember sulfate, or maybe we remember, sulfate is a -2 charge and there are 2 of them. So that's a total of -4, but I'll write it out. So there are 2 sulfates with a -2 charge. And we know that all ionic compounds have to equal 0 total charge. So this becomes an equation where we solve for X. So if we solve it, X is equal to 2. So the full formula is Na2MgSO42. Yep. And so the X represents how many sodiums there are. And so we wouldn't need a parentheses for that. So sulfate is an example of a polyatomic ion. So one single sulfate has the total -2 charge. So the entire SO4 cluster of atoms has a -2 charge. And that's going to come up in a few slides. So we will have an example of that. Oh, whoops. There you go. Now, another question of what is the formula of the compound made from oxygen and magnesium? So this is going through the steps. Can we do it one more time, this time with 2 different elements? Actually, one of them is the same. So do it with me. So oxygen and magnesium. So remember, there is an order for this. Metals or positive ions go first. So we're going to put Mg and we're going to put O. Then we are going to write their charges. So magnesium, what charge does magnesium predictably make? 2+. What about oxygen? So again, if this is tricky, go back to the periodic table. Remember, each column on the left and the right has a predictable charge. So magnesium is in the second column. It's going to be a +2. This is going to be -2. And then we're going to crisscross them. Crisscross. So what I'll do is I'll write Mg2, or maybe I'll emphasize the, I'll emphasize the color as well. So I'll do 2. So here is the result of our crisscross. But here is the tricky part. When we're done with the crisscross, we always have to check, is this an empirical formula? And some of us have already gotten that part. No, it's not. So what do we have to do? Pull out the common 2, divide by the common 2. So do. Maybe I should have done them separately. Maybe that would have been better. Just to make it clear what I'm doing. Divide by 2, divide by 2, which means my answer is actually MgO. Or in other words, it's a 1 magnesium to 1 oxygen mole ratio. So that's the one tricky part. At the end, you have to ask, is this an empirical formula? And if it's not, we have to reduce it. So this leads us to a sort of pitfall in doing this. Because empirical formulas can be reduced, we cannot always, students like to think of it as uncrisscrossing, to find the formula of the ions. So if I were to say, oh, can you tell me what the charges are for magnesium and oxygen just by looking at this formula, it's actually ambiguous, right? Unless we already knew the answer because we know the periodic table, which is something we should do. Because it might suggest to us that magnesium and oxygen both have 1 charge, +1, -1. So for this reason, we cannot safely do what I call the uncrisscross every single time. It is possible to do it with some compounds, but we need to be on the lookout for, are we sure based off of what we've memorized about these ions? Are we certain that magnesium is going to be plus whatever? And that's when we should memorize. The foolproof way to do it is actually to do the setting up the equation. All of the positive charge and all of the negative charge have to equal 0. So if you know the predictable ion of 1, so for example, magnesium is +2, and you know there's one of them, plus we know oxygen is -2, and there's one of them, it should add up to 0. So if you don't know the charge of one of the ions, and like I did in the previous slide, you could set it up like an equation where there's a single x that you don't know, and then verify what the charge is going to be. And so we should be able to do this by the end of this section of the course. So let's try it. What are the ions with their charge in the following? So I'm going to give you a compound and you tell me which ions it has. And this example sort of shows us that in this case, it is kind of possible to uncrisscross these species, because if this 2 is down here, it meant that I made the crisscross to move it from the upward position. And since selenium is a nonmetal and it's the last element of the compound, it should be the negative ion. The negative ions always come last in the formula. But we should have memorized that selenium is -2, hopefully. It's part of that -2 chalcogen column. So let's try it. If I have CaF2, what are the ions with their charge? So again, this is about sort of recognizing the formulas, and hopefully we're getting that down. Calcium. So this has calcium and fluorine in it. So calcium is the +2 ion. Whoops. And fluorine is the -1 ion. So, and in this particular case, it was possible to uncrisscross them, right? The 2 goes up. There's an invisible one goes there. In this case, you could have done that. And then get the answer. So what this means is that as far as like a particle representation, there's a calcium 2+. Oh, actually, yeah. And then minus. So there are 2 ways that we know that calcium is a 2+. We have memorized that calcium is an alkaline earth metal, and therefore, as part of the second group, it carries +2 charges in ionic compounds whenever it forms an ion. Or we could have done it by process of elimination if we already knew fluorine. In this case,
Professor.
Yeah.
I just had a question because I'm trying to put this together. The predictable charge of alkali metals, for example, of a 2+ charge, does that also correlate with its positioning for on the periodic table for electron configuration?
Right, it does, because the alkaline earth metals are in the S block, and they're all of them end with S2, 2 electrons in the S valence orbital. So its last orbital has 2 electrons, so they want to get rid of those 2 electrons. So all alkaline earth metals want to become +2 ions to get rid of those last 2 electrons. So that's a nice sort of correlation. But if we didn't know what calcium was, but we knew what fluorine was, we know fluorine is a halogen and those make -1 ions, then we can set up the equation, well, 1 calcium plus 2 times the -1 charge should be equal to 0. So where did this come from? There are 2 Fs, and fluorine wants to make a -1 charge. So if we solve this equation, we would get that calcium is equal to +2. And so that means CaF2 contains the calcium 2+ ion and the F- ion. And if we wanted to go the other way, if we knew calcium was the +2, we could set up an equation to solve for the F as well. So it works both ways, as if you know one, you can solve for the other. So how about we try it one more time with AlBr3. Again, the task is, what are the ions in this formula? And you should have the periodic table. Don't be afraid to reference the periodic table. Where is Al? Where is Br? So it's going to be the Al3 plus ion and the Br minus ion. So this compound, if I were to zoom in on its particles, I would see a repetition of 3 plus aluminum and 3 minuses. And then that would repeat over and over and over again. It would not exactly look like this. I'm not saying it would be perfectly like this, because, you know, in real life it looks a little more complicated. But the general idea is that ionic compounds are repeating patterns of a specific sort of unit. And so the specific repeating pattern is going to be the aluminum ion with 3 bromide ions repeating over and over and over in a crystal. And now what about the last one? What are the ions in BaO? This is going to be the Ba2 plus and the O2 minus. This is one where we have to be careful, because if we just look at them, we might think maybe they're +1, -1. But this is a case where we've reduced the crisscross. We crisscrossed them and then reduced it because there was the common 2. This is an example of why it's important to not rely too heavily on, oh, I can always uncrisscross the subscripts to get back what charge it had. In this case, what we did was we did this. Ba2O2, and then we divided by 2 because there's a common 2 there to get that. So this is the sort of warning example that if the question were, what charge does this ion have inside this formula, we have to be careful because empirical formulas are always reduced. So their crisscrosses might also be reduced as well. So now that we know how to predict the formula of ionic compounds, we can go ahead and ask, well, how do we make ionic compounds in the lab? So what would be the recipe to make them? If I had, say, calcium and fluorine available, how would I come up with a recipe to put them together? And so for that, we're introducing, for the first sort of real-time, chemical equations. So a chemical equation depicts metals and nonmetals forming ionic compounds. So a chemical equation, what we sort of represent, and we saw this a little bit in the last lecture, we have sort of our starting material, or kind of we can think of it as our ingredients. The arrow tells us what they become, or the products. So what we can do now that we know how the ionic compounds formula should be formed, what ratio they should be, we can start to write recipes in this sort of symbolic format. We're going to put the symbols for the elements that make them, and they become the ionic compound that we desire. Now, a couple things, much like in a recipe, it's important to designate, say, if you're baking, whether you're using granulated sugar or powdered sugar or brown sugar. In the same way, we also have designations of what phase the substance is going to be. So we have G for gas, L for liquid, S for solid, AQ means aqueous, which is dissolved in water. The arrow means produces or makes. And the arrow with a delta symbol means you have to heat it to make your product. So what we're going to do is we're going to write symbolic recipes using chemical equations that tell us how the elements come together to form ionic compounds. So I know the formula for sodium chloride, but what is the recipe? How much sodium and how much chlorine in terms of atoms is necessary to make this? But before we do that, we're going to be combining the elements. We have to remind ourselves that some of the elements actually have special symbols, and it's hint, hint, the diatomic 7. So the diatomic 7, we need to remember which ones those are. So remember that diatomic 7 means the phase and the particle that we have at room temperature here on Earth. And so we remind ourselves that's going to be hydrogen, and then the 7. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Have no fear of, how does it go? Have no fear of ice for the ice cold beer. If you don't like beer, you can replace it. Ice cold brownies. Ice cold. Brownies probably don't taste good, ice cold. But I'm sure we could think of a different one. But with this, we just have to remember that if we're combining the elements to make ionic compounds, we just have to make sure if I were to take a bottle of this element out, what would its symbol be? So this is why we're emphasizing this right now. The halogens, nitrogen, oxygen, and hydrogen are my diatomic 7. These are my, oh, maybe I should say H. Maybe I should just say X. This is my X2. Now about the phases. So it's actually easier so the majority of elements are actually solid at room temperature. So so it's actually easier to designate which ones are not solids. That's actually an easier question to answer. So remember that we have a group called the noble gases for a reason. Noble gases, emphasis. It means that these are all gases. So typically we don't include OG just because it's radioactive and there's not enough of it on Earth to actually become a gas. It's just atoms that then disappear. They go through radioactive processes. So we typically don't include OG, but it's the noble gases. And then chlorine, fluorine, oxygen, and nitrogen are also gases, as well as hydrogen. So it makes kind of like a nice little cluster to help us. So blue is our gases. And then there are only 2 liquid gases. There are only 2 liquid elements on the periodic table at room temperature. Those are going to be bromine, which I'll emphasize because it's kind of hard to see. Bromine and mercury. Whoops, and we know that because we have the gas chapter where we used liquid mercury to test the pressure of gases, because mercury is very heavy. So we have that. So this is at room temp. And the rest are all solid, so solid. So our gases are the noble gases, and then the majority of the diatomic 7, but not all of them. So the majority of the diatomic 7 and the noble gases are gases. There are 2 liquids, bromine and mercury, and the rest of them are solid. So with that, we can write recipes for how to put together ionic compounds. So that's really nice. Okay. So let's try it. So keep this in mind on our periodic table. So we call this ionic synthesis. Synthesis means make. So, so typically when we're making ionic compounds and doing most of our chemistry, we're doing it at room temperature. So, and typically room temperature is considered 25 degrees Celsius. So unless otherwise specified, we're going to go with room temperature elements. So synthesis means we're making the elements from the compound. I'm sorry, we're making elements form the compound. So we're putting together. And the opposite of it is going to be just the reverse, decomposition. Ionic compounds separate back into their elements. And so it's going to be ingredients or reactants on one side, products on the other side. The only thing is that all atomic recipes have to also obey conservation of mass, or there needs to be the same number on both sides. So in some cases, we're going to have to write coefficients, but we'll see how that works in a little bit. So let's try it. Let's write the synthesis of magnesium fluoride from its elements. So we're going to say magnesium fluoride, that's magnesium and fluorine. So we're going to say Mg, and now we're going to put the symbols for their phases down. So magnesium would be solid, and I like to put it as a subscript. So that means magnesium is a solid. Plus, now what element symbol do I put for fluorine? We're going to go over here. Okay, here's F. It's gas. Also, I've highlighted it. Why did I highlight it? Because it's F2 gas. And we say that they make the compound between them. So what are we going to do? We're going to, maybe I'll jump back to it. The formula for the ionic. Determine the predictable charges of the ions, write the symbols, and crisscross. Reduce if necessary. So I like to do this on the side so that I don't make a mistake. So I'm going to put Mg and I'm going to put F. The charge of Mg, so let's look at it. It's actually in the second group, the alkaline earth metals, plus 2. F is minus. And so we crisscross them. Our result is going to be Mg F2. Now, what phase of matter should an ionic compound be? Solid. In one of our first slides, we said has high melting point. So this would be our recipe for how to make magnesium fluoride. We're going to take magnesium solid and diatomic 7 fluorine gas, and it makes a crystal that has MgF2 in it, solid. And so that's the synthesis of magnesium fluoride. We're going to put together magnesium metal and fluorine gas, and it's going to make crystals of magnesium fluoride. There's some really cool videos for making ionic compounds from elements. For example, adding chlorine gas to sodium metal and watching the salt crystals form. And so, if I think I put a few on the module, but if I haven't, then I want to put that because it's a really nice visualization. Yeah, and so they grow in a really impressive way, sort of like plants growing. And for our purposes, all ionic compounds are solid. Only if you're talking about sort of advanced material science do you ever get into different phases of matter at room temperature. Ionic compound, although there is a big exception to that, and that's actually LCDs, right? LCD displays, like your computer screen or your TVs. In fact, you can probably touch it right now and see like a ripple happen on your screen. That's actually an example of a special kind of ionic compound that is actually liquid. So LCD stands for liquid crystal display. So these are actually liquid crystals. And that's a whole other thing. That's like, more advanced physics and material science. But this is the starting point. Chemistry is a branch point for a lot of different fields. So, I'm emphasizing to people all the time that, maybe you didn't consider chemistry to be sort of something you might want to pursue, not necessarily as a major, but chemistry actually branches out and can get your foot into in the door to a lot of different fields, including biology, physics, material science, different types of engineering, and so forth. So, something to consider. And if you'd like to talk about it more, feel free. Now, how about the decomposition of sodium sulfide to its elements? All right. So this time, decomposition means break apart. So we're starting with the ionic compound and we're going to break it apart. So our first step is to write the ingredient. In this case, we're breaking apart starting with sodium sulfide. So sodium sulfide comes from sulfur. So again, in order to get the representation correct, and this was part of the pre-lecture to sort of figure out how to interpret the name, though we'll cover that next. Sodium sulfide comes from sulfur. Sodium is a plus ion by its predictable charge. Sulfur is a -2. And so we're going to crisscross them. So that means the formula is Na2S, solid. So that's going to be the ingredient. And what we're doing is we're breaking it apart. So it's going to break apart to become, so the arrow means become or makes or produce. And now we turn it back into separate elements. So we're going to separate it into, in this case, 2 elements. Sodium is going to be, what is its formula? Na solid plus. And again, because most of the elements are solid, except for the ones we designated gas and the ones we designated liquid, and pure sulfur, solid. So this would be our unfinished formula. Now there is one other consideration, and that has to do with the yellow box. If we sort of interpret what's going on here, it means there are two moles of sodium for every 1 mole of sulfur, or 2 atoms of sodium. So plus, and then the 2 minus. But, and maybe I should color code it. So maybe this is the blue. But we've returned to 1 sodium. And 1 sulfur. So there is a tiny problem in that this recipe has some of our atoms disappearing all of a sudden. So that's where this yellow box comes in. We can add a coefficient or a number in front to make sure the recipe makes sense to us. Atoms cannot just disappear or appear out of thin air. And so if we had 2 sodium atoms that we started with, and we put them into the reaction, we need to have 2 come out. And so for that reason, we put a number in front to make sure the numbers add up. And in this case, we put a 2. 2 sodiums inside this substance become 2 sodiums outside of the substance. That's what we call conservation of mass. Atoms need to be present on both sides. They can't just disappear. They can't just reappear. So as far as a recipe goes, it tells me that if I take a mole of sodium sulfide, I will get 2 moles of sodium and 1 mole of sulfur. And then as far as where my phase labels go, remember the easiest thing is every element is solid, except for the gases, which are parts, pretty much this little corner and hydrogen. And then there are only 2 liquids. Everything else is solid. But that is how we would represent making an ionic compound from its elements and then breaking an ionic compound to its elements. So yeah, so most metals, metals are pretty much guaranteed to be solid except for mercury. Mercury is the only liquid metal. So if you have a metal, it's going to be solid at room temperature unless it's mercury. Okay, but that is making and breaking ionic compounds. You now know your first chemical reactions, how to make an ionic compound and how to break an ionic compound. We put the elements together to make, we split the elements apart to break. Now, I trust that we watched or are in the process of watching the pre-lecture videos, because that's where I go into a lot of detail on how to identify the ionic compounds and name them. But I do want to, just in case, talk about it a little bit. So naming binary ionic compounds. So we identify nonmetals and metals, and to piece together how to name an ionic compound, there's a certain formula to it. Nonmetals have their name changed. The ending of their name becomes "ide." So this is why instead of calling it sulfur, I called it sulfide. Because once sulfur becomes a part of an ionic compound, we say sulfide. That's just to designate to the reader that we're not talking about pure sulfur anymore. We're talking about it combines to make an ionic compound, an ion. The predictable metals, which we should be comfortable with, right? The alkali, the alkaline earth. And then don't forget the little zigzag, or it's not a zigzag, it's like a diagonal. Aluminum, zinc, and silver are all predictable metals. They just say their metal name. There is no change to it. So if my ionic compound contains sodium, it's always going to be called sodium. If my ionic compound contains aluminum, it's always going to be called aluminum. But the non-metal, the ones that are on the right, the partner, they change their last name to "ide." However, variable metals are all others that I have not mentioned here. Those need the Roman numeral or old name that I mentioned in the pre-lecture videos that indicate the charge. And what do I mean by variable metal? It means that it does not have a predictable charge. And an example of that would be, say, lead. So lead can come in 2 different forms, a +2 charge ion and a +4 charge ion. Because it's variable, it depends, we have to let the reader know which one we are talking about. So if my compound contains lead with a +2 charge, I call it lead 2. And so we say Pb2+ would be lead 2 with a Roman numeral. There is also an old naming convention that we need to know, and that was also covered in the pre-lecture video, where we use the sort of Latin names. So lead 2 would also be called plumbus. Oh, I think it's us. There we go. Oh, I misspelled it. Hold on, don't spell it yet. Plumbus. So that's what I mean by the variable metal. So when we combine the names to make an ionic compound, the metal is usually its own name, except if it's a variable metal, then it has a Roman numeral or an older name. And then the nonmetal, we say the nonmetal's name, but it just has the ending "ide." So this is why we had things like, in the previous examples, sodium chloride, sodium sulfide, magnesium oxide. So that's how we name ionic compounds. Now I mentioned C table because in the video and in the module, I have a downloadable table of how the naming works for these examples. So I gave you the example of lead 2, plumbus. All of the other ones you need to know are in that table in module. In this case, we're in module 7. Module 7. So that is going to be the go-to place. Whenever I'm talking about ionic compounds, we need to make sure we understand what we're talking about. So I'll be telling you about, say stannic fluoride. You should know what that means. Tungsten 3 chloride. You should know what that means. So that was all part of the pre-lecture. Again, it's really more beneficial to take your time, maybe during the weekend, to sort of go over those. And also keep in mind, CP 7.1, I actually have a combination of, I think, 5 different videos where I'm just kind of with flashcards with you. I say, if I made a compound of sodium and sulfate, what is the name of it? And you can speed through those if you want. You can pause them and sort of practice, but there's a ton of practice on CP 7.1 of how to name and identify ionic compounds, okay? So we should be it should be something we're doing at the same time. We're doing the lectures together, but then you compare it to what's on the practice that's on the CPs, okay? So I feel like maybe this is sort of like a sense of panic, like, oh no, this is a lot. There is practice on those guys. So let's first try a little bit of practice of naming, and then figure out the more sort of trickier ideas. So what are the names of these binary, meaning 2-element ionic compounds? So this one would be called, this is potassium. It is a predictable ion. Maybe I'll write that. Predictable. So it's potassium chloride, okay? Again, chlorine, drop the ending "ide." This is calcium sulfide. All right. This one, now where is Cu on the periodic table? Now this is where we have to be careful. So this is going to be copper 1 fluoride. Why is it copper 1 fluoride? This is not a metal with predictable charge. So because it's not one of those predictable, and remember the predictable are my group 1A, group 2A, and then aluminum, zinc, silver. Those are the predictable ones. Copper is not part of that. So because we say it's a variable ion, we have to tell the reader what the charge of this ion is. So fluorine, this requires our sort of skill of deducing charge. Fluorine makes -1 ions, therefore copper must be a +1 ion. So we say the Roman numeral for the 1+ ion. So this would be its name. Or the Latin version is going to be cuprous. Fluoride. Fluoride is a very hard word to spell because it actually looks kind of backwards. It's UO, RIDE. What I tell students is that if I were to ask you for the name, you can give me whichever name you want. Copper 1 fluoride and cuprous fluoride mean the same thing. However, I am going to use both. So you can use whichever name you'd like. However, you should be able to understand me when I use either one. Okay, so to recap which ones we have: potassium chloride, calcium sulfide, copper 1 fluoride, or cuprous fluoride. And then this one would be Ag. That one's the kind of tricky symbol because it's actually silver oxide. So silver oxide. Just to go back and double check, again, the predictable metals are alkaline earth, aluminum, zinc, there it is, silver. It means that the metal has no name change. Just say it. So that means this one is going to be silver oxide. And that's all there is to the naming of binary compounds. The subscript is not part of the name. So notice it doesn't matter that I have a 2 here. It's called silver oxide. All that matters is whether it's predictable or not. And if it's not predictable, and by that I mean it's one of these other metals, then we have to use a Roman numeral or an old Latin name. But otherwise, it's very formulaic. Metal-ide, metal something-ide. Polyatomic ions. Polyatomic ions are those in which atoms are bonded together and as a group become an ion. So this is different than before because we're talking about single atoms, a single dot that is now has a plus or minus charge. Polyatomic means many atom. So poly means many. So polyatomic ions are those in which there's more than one atom and as a group, they have a charge. Our first stop is the oxyanions. So they have the formula, they have some non-metal, typically, in their formula. So this is the X. And they have one or more oxygen atoms. That's where the word oxy comes in. And then anion, because there's a charge on them and it's a minus charge. So these are the polyatomic oxyanions. It's a nonmetal stuck together with some oxygen atoms that has a minus charge. And so this is what I call the core list that I mentioned in the pre-lecture videos. These are the 8 ions because these ions all end in the name 8. carbonate, CO3 2-, nitrate, NO3-, phosphate, and so forth. So phosphate, sulfate, chlor. So all of the halogens have their own ate. It's chlorate, bromate, iod. Actually, I should put bromate, iodate, and chromate as the last one, which is a little bit different because it. So the way it works is that instead of our simpler picture where it is one circle with one circle, a polyatomic, it means that it's just a bunch of circles, but they're doing the same thing they did. The only difference is they have a different kind of bond between them that we're going to talk about in a couple lectures called a covalent bond. So these atoms are stuck together, but together, you see the bracket, they make a minus charge. And so a positive will stick to this cluster that has a negative. And the ionic bond is what's keeping it together. So remember, it's an invisible attraction between positive and negative that we see. So those are our polyatomic ions. The difference being that they have oxygens attached to the nonmetal. Now, this is where it gets a little bit confusing because some students forget about them and they often try to think of oxygen as being a separate entity. But this is why I want to emphasize them right now. When you look at formulas for compounds, there are certain sort of, much like you memorize how to read by, not by sounding out every individual letter, right? That's not how we read usually. What we read is we've memorized what clusters of letters go together to make a word. So when I'm reading the word water, I'm not reading W-A-T-E-R. I'm actually seeing the word as a whole and say, oh, that's water. In the same way, when you start looking at formulas and seeing examples, not just in the textbook, but in real life, we want to say, don't think of it as C's and O's. Think of it as a CO3. Okay, the same idea. Focus on patterns that we're seeing here. And so for this topic, flashcards are an amazing resource for that. To be able to recognize, just like, I mean, to be honest, isn't that how we started to learn how to read back in, school, grade school? Yes, you learn the alphabet, but then when you're learning words, you're learning to see them as units. And that's what we want to do here. Nitrate is NO3-. It's not NO3, it's not individuals. We think of them as a cluster or as a group. And so for emphasis, we say, we have some examples. Now, the thing is, because polyatomic ions represent a single entity, a single unit, when we're talking about multiples of them, this is when we have to use parentheses. And so here are some examples. This is magnesium. And then if we go back to the name of this, again, I'm not going to say sulfide oxide 4 or whatever. I'm not going to do that. We want to recognize them as a unit. So if I go back one more time, SO4 2- is sulfate. And that's what I want to recognize. So we have magnesium, and then I say, oh, I see this. I see the pattern here. This is magnesium sulfate. And so it's indicating that there's a magnesium ion, and then we want to recognize there is one sulfate unit there. Not individual S's and O's, it's a sulfate. Just like water isn't a W and an A and so forth, it's a water. And then the same thing, if in our formula we needed, say, 3 nitrates, this is where we say, I just don't need 3 N's, I need 3 of everything. So in this way, we put the parentheses to make 3 nitrates in the formula unit. Okay. And then the same thing, I have this formula, zinc phosphate. I need 2 phosphates, so I'm putting parentheses around them. So this is how we do the formulas with polyatomic ions. We want to think of them as a cluster or as a group, and then we're good. And so this means there are 2 phosphates in that formula. Okay. Now, there are actually quite a few oxyanions that we're going to memorize, but I don't want us to necessarily start by flashcards for every single sort of option. There is a method to the madness. There's a trick to it. And so that's something that I go over in the pre-lecture as well. But there's a pattern to change a certain ion into a different kind of oxyanion. We started with the list I showed before, the 8s. And so that's what I consider the core list that you should know. The rest of them, I encourage you to memorize by pattern. An 8 ion becomes an ite ion when we take away an oxygen from the formula. If we take away a second oxygen, it becomes a hypoite ion. If we take the 8 ion and we add an oxygen to it, we become a per-8 ion. And if we take one of the ions and we add a hydrogen ion to it, we add H+ to its formula, it becomes a bi-ion or a hydrogen ion. So as an example, we can have SO4 2-. This is sulfate. If I take away an oxygen from it, I get SO3 2-. It becomes sulfite. That's how it works. So my recommendation is to memorize the 8 ions first and then use the pattern to get the others. If I take this and I add H and a plus to it, I get HSO4-. This is bisulfate. And yes, CP 7.1 has a series of extra videos where I flashcard you through naming these. So I would recommend maybe a flashcard website for generating these or finding one. But I have videos where we're going through what is the name of this and this and this. Okay, and then that's what the pre-lecture videos were for, so that you get this information there as well. So maybe this is a little too early to do this because I have this feeling that we didn't watch the pre-lecture videos. If that's wrong, then I'm sorry, I apologize. You're amazing, I love you. But if you didn't, then go watch those videos because this is very confusing if you didn't watch it. But for the purposes of having this recorded so that you have the answers when you're ready to watch, let's practice these names. So let's get the formula of zinc sulfite. Oh, no. I didn't mean to do that. There we go. So again, remember, we take apart what this name means. Zinc means zinc ion. Sulfite means sulfite ion. So that's going to be Zn. Now the ion, let's look at the periodic table. Where is zinc? It's a predictable 2+. Sulfite. So again, we remember sulfate is the one I'm going to memorize. This is my 8. Ite means drop 1 oxygen. So that's going to be SO3, 2 minus. What am I going to do? Crisscross. How is that going to look? ZN SO3. What happened to the 2's? Remember, I drop them to the bottom and then I say, can they simplify? And they do. The 2's reduce to 1's. Nickel bicarbonate. Nickel is Ni. What does the 2 mean? A 2 plus. So we have carbonate, CO3, 2 minus. What does bi mean? Add an H plus to it. So that means bicarbonate is HCO3 minus. So that means that goes there. HCO3 minus. What am I going to do? Crisscross. Oops, maybe do that. Now here's where it gets, we have to be careful. So Ni gets a 1. HCO3. Now the 2 goes here, but what does this 2 mean? It means I have 2 of this guy. So I have to say that. I have 2 of everything. So that's where that goes. With a parenthesis to say I have 2 bicarbonates. So that is how we would do it with a polyatomic ion. Now to do the opposite, it requires the opposite thinking, which again, this is new. We might not have it down perfectly, but we go by, okay, name the first and then name the last. So this is going to be calcium. And then this, remember, this parentheses is telling us how many there are. It's how, what is this guy? So this is, again, my recommendation. Start by memorizing your 8 ions and then use a pattern. So according to, oh, whoops, I went too far. Sorry. In this case, Br, the halogens, their 8 ion has O3 minus to it. So in the case of replacing for the correct, this is going to be bromate. Ooh, someone already got it. So that means we use the pattern. Oh, so I'll go back to that. So that means we've memorized BrO3 minus is my 8. And now I use sort of the information. 3 oxygens is an 8. This has 1 oxygen, so there's 2 less. So again, we use our pattern. Take away 1 oxygen and it's an ite. Take away 2 oxygens and its name becomes hypo blank ite. So that's what we mean by we're going to memorize that pattern. So that means that the name is calcium hypo bromite. Now this one, the final one, what is it going to be? I'll leave you to think of it as I... That one's going to be manganese 6, Roman numeral 6, nitrite. NO3 is nitrate. 1 less O is a nitrite. So manganese 6 nitrite. Why is it 6? Because I know that nitrite is going to be a -1 charge because we are going to memorize that. So by process of elimination, or deduction, I should say, if I need 6 of these to balance out 1 of these, that's 6 minus charges, means that manganese by itself must have a +6 charge. So this would be manganese 6 nitrite. Whew. All right. I think we're at a good stopping point. So I will cut the video off here since it's getting kind of long. I think I took too much time on a couple of slides. But okay, we're going to memorize these naming conventions. So stay tuned for that. Stop the recording.